Okay, so we're going to round out our sort of named time-dependent quantum mechanics equations with something that's called the Heisenberg equation. And the basic idea here is that we want to know about an equation of motion for a Heisenberg operator. So remind yourself what a Heisenberg operator is. When we looked at the time-varying, I wrote it in the last lecture segment, right? It's this U dagger, dt naught, operating on this, what we'll call AS for Schrödinger picture operator, which if you want, you can think of it as the ordinary way that we think about things. All right, and this is what we mean by a Heisenberg operator, A sub h of t. Okay, so if we have A sub h of t, it should have time dependent. We should have an equation of motion for that. And sometimes it's quite informative to consider a Heisenberg operator. This turns out to be incredibly important for response functions because we'll think of the dipole moment operator as being written in the Heisenberg picture. Okay, so what we want to do is we want to compute the time derivative of AH. Okay, and so there's nothing magic here. There's a couple cute tricks that I really like that you do in this derivation. But otherwise, it's mostly a plug and chug kind of thing. We do need to keep track of how to use the product rule for these the three terms that we'll have. But other than that, nothing too fancy, except we will also allow that there's some possibility that the Heisenberg operator, the Schrödinger picture operator might itself have some time dependence. Imagine it was an electric field, for example. Then it would have a time-dependent, maybe, oscillation or whatever. Okay? Maybe it goes up and down. Maybe it's not oscillatory. Anyway, it's possible for the Schrödinger picture operator to have time dependence, so we have to include that explicitly. Good. You'll see how it comes out. It's very straightforward. So we take the derivative of this thing, U dagger. I think I'm going to save myself a little bit of writing and just not put the t's and t naughts in there. It should be pretty straightforward. Whenever you see a u, imagine always there's a t and t naught in there. We will worry about the AS itself. So this is going to be this equation, 3 terms. So use the product rule. So it'll have the first term will be du dt times the product of the other two plus u dagger times the derivative of the inner one. And remember, if the Schrödinger picture operator doesn't have time dependence, this term goes away. So only if you have this. All right. Then the third term is u dagger AS times the time derivative of u. Okay. Now, what do we know about the time derivative of u? We just did this like 2 seconds ago, right? Well, I did. You might have seen it a while. Who knows? We're going to use the Schrödinger equation. We're going to use the Schrödinger equation for the time evolution operator, something that we derived a while ago and used again last time. Just keep track of, this is the dagger one, this is the normal one, right? So the dagger one is going to be plus I over h bar, okay, and then h, and then u in this order. All right, so this is what's in this parentheses here. Then as, then u. The middle term, nothing happens with the middle term. So I'm just going to leave it like this, all right? So there you are. So I'll have to just keep bringing it along with us. In some notations, they kind of simplify this a little bit. Okay, and then we have the last term, u dagger AS, and then we plug in the normal Schrödinger equation, so that's minus I over h bar, and then h times u. Now this h is the real h, right? Whatever h is. Okay, so now what we're going to do is take stock. So what we have here is, there might be something wrong. This is h dagger, this is u dagger. Right, always look for some symmetry. There's an u dagger here and a u here, AS, u dagger, u, and this should be backwards. So I did everything exactly wrong, even though what I said probably was correct. So that's very funny. Hopefully you noticed that. All right, so this is actually u dagger h AS. Very good. Okay, so this is the term in parentheses. All right, so let's see now what we can do with this. It looks like we haven't really made a whole lot of progress, but I'm going to pull over the terms that are sort of the interesting ones. This is the least interesting because this is just the time dependence of the operator by itself. Let's bring these over. So we have I over h bar times u dagger h as u. Now this is a plus I over h bar and I have a minus I over h bar. So I'm going to put a minus sign here. The I over h bar has been factored out, and I have u dagger as h u. Okay, so this should look pretty reminiscent of something that we saw with the Liouville-von Neumann equation. We have a term that looks like itself minus the other ordering. So it looks kind of like a commutator. It's not a commutator yet, but you'll see in a minute that we can turn it into one. All right, plus u dagger u. Okay, good. Now what do? We insert. This is one of those cases where we have a clever use of the inserting of the number 1. You can always insert the number 1 wherever you want. Now if I insert the number 1 with a number 1, nothing happens here. Well, I'm not going to do that. I'm going to insert the number 1 in this way by writing u times u dagger. Remember that u dagger, if u is a unitary matrix or unitary operator, u dagger is equal to u inverse. So u times u inverse gives us the identity operator. So I put that in both cases. All right, when I do that, what do I get? So I'll bring this up here. I have I over h bar. I have u dagger h u. I have u dagger as u minus u dagger as u, u dagger h u. Right, that's my first term. Wow, that's a terrible h, isn't it? This is part of the reason why I like to say what I'm writing out loud, because even if I make a right-o, or if you can't read what I'm writing, at least you hear it. So that's u dagger u. Of course, I need the other u. Okay. U dagger h u. Good. Plus the term we can't do anything with. All right, so what do we notice about that stuff in the square brackets? What we notice is this is the Heisenberg representation of the Hamiltonian. So I'm going to put a little sub h on it with a t. This is the Heisenberg representation of A, so I'll call that A sub h. And this is the other way around. So this is AH, and this is HH. Okay, so what you can see then is this is obviously the commutator. So this is I over h bar times the commutator h with A plus the extra term. And in many cases, the extra term will not be there because you will be in the common case where the operator itself doesn't have any time dependence. This is called the Heisenberg equation. And it's interesting if you notice these different things. So this is an equation of motion for an operator, right? An observable quantity. We had the density operator, sorry, the Liouville equation, Liouville-von Neumann equation, the equation of motion for the density operator. And we have the Schrödinger equation, the equation of motion for the wave function or the state vector, the state of a system, right? They're all essentially different reformulations of the same fundamental thing. They have different roles. The Liouville equation will look quite different when the density matrix is not represented as a pure state, when you're not talking only about wave functions, single wave functions. That's very important. Heisenberg, this was his actual sort of statement of quantum mechanics. Schrödinger had his own statement of quantum mechanics. And again, it was Dirac who kind of showed that these things were all like different versions of looking at the same thing. And I think that's why this term Heisenberg and Schrödinger picture has stuck, because they aren't different things. They just are different ways of projecting the information out.